In the last video, we took a look at how to graphically add and subtract vectors, and now armed with that, we're finally ready to dive into acceleration. So acceleration, like the other quantities, is a vector quantity, and it is defined to be the limit of ever decreasing time intervals, the time rate of change of the velocity of something. So the dimension of this is going to be length per time squared. So typical units would be things like meters per second squared, for instance. So this is the time rate of change of the velocity. And the first thing to realize is that the acceleration does not necessarily point in the same direction as the velocity. So as an example here, let's first start by thinking about a car that is speeding up. Now here, as the car speeds up, let's just pick two velocities, say here, we'll call that our v initial, and here, we'll call that our v final. Now here we know that the acceleration will always have to point in the same direction as the change in the velocity. This is because the time interval will always be positive, so we'll be multiplying by a positive number. So let's go ahead and find our delta v, and then we can recognize that our acceleration would have to point in the same direction. So remember, the change in velocity is v final minus v initial. So here I will, by head to tail, I will add negative v initial to v final. So v initial points short and to the right. So negative v initial would point short and to the left. So I put the tail of v initial onto the head of v final. Strictly speaking, I should put the one right on top of the other, but then the diagram would get cluttered. And my resulting change in velocity points here to the right. Now the acceleration will always point in the same direction as the change in velocity. So I will draw my acceleration vector to be in the same direction. Now the length of the arrow you draw does not matter with regard to the length of the arrow you draw for the delta v, as long as they're proportionate if you've got more than one of them. This is because acceleration and velocity have different units. And since they have different units, you can't meaningfully compare the length of the arrows that you draw. So you can draw them however you want to be sensible to you. In this case here, what we see is the acceleration points in the same direction as the velocity, which is telling us that the velocity vectors are getting longer, which tells us that the object is picking up speed. Okay. Let's try a different case. Let's think about a car hitting the brakes. So it'll have started by going relatively quick and then end by going a little slower. So here's my v initial, and let's pick this one here, a little shorter to be my v final. So again, remember that the change in the velocity is always going to be v final minus v initial. So here's my v final, and I will add to that negative v initial, and then the resultant goes from the tail of what's left to the head of what's left. So here is my resultant delta v, and the acceleration points in the same direction. There we go. I just want to show, so here what we see is that the object is going to the right, but it's slowing down. So here the acceleration is anti-parallel with the velocity. And when the acceleration is anti-parallel, that tells us that it's slowing down. But I do want to show that it can be even more complicated than that. So let's just think about for a moment. So truly the acceleration can point any which way with respect to velocity. So let's just take a look at a case of a car going around a curve at a constant speed. So then say something like this would be my V initial, and something like that would be my V final. So I can add to that, so I can say, all right, delta V is V final minus V initial. So I'll go ahead and draw in my V final. There it is. And I'll add to that negative V initial, pointing in the opposite direction. So my delta V here would be pointing like this. So the acceleration in this case is pointing right into the center of the circle when we're going at constant speed. So we'll do more with that later. For now, we'll just constrain ourselves to just one-dimensional motion. And one-dimensional motion, if the acceleration is parallel, you're speeding up, and if it's anti-parallel, you're slowing down. But I want you to be aware that in general, the acceleration can point any which way with respect to the velocity. And we'll see that the perpendicular pieces of the acceleration tell us how something is going around in a circle. Okay, so now let's start to think about this more graphically. So again, if we go back to our definition, we said that's the limit of delta V with respect to delta T. And since we're working in one dimension here, I'll just drop the vector signs. Whoops. In one dimension and just say it's the limit as delta T approaches 0 of delta V over delta T. And if we think back in analogy to what we did when we defined velocity, which was that V was the limit as delta T approached 0 of delta X over delta T. There we saw we could interpret the velocity as the slope of the tangent line of the position time graph. So this tells us exactly the same thing, that the acceleration equals the slope of the tangent line of the velocity time curve. So let's look at a few specific cases here. So for instance, I could go ahead and have a graph of, let's just start with the V versus T graph here, where V increases steadily with time. So here, the value of the velocity is positive. And if I go and look at the slope of this, the slope is also a positive number. So this is the acceleration is positive. So in this case here, you would say that the velocity vector is pointing to the right. And similarly, yeah, that's good. Similarly, we can say that the acceleration vector is also pointing to the right. Okay. Let's do another one. So we'll copy that, paste that, move that down there. All right. So now let's look at the velocity being positive, but instead of the curve sloping up, it slopes down. Like so. So here, the slope is negative. With the slope being negative, that would tell us that the acceleration is now negative. And that would tell us that the acceleration, now points to the left. Okay, we can do some more of these. Why not? So let's say the value of the acceleration were negative. Something like that, VT. We can have the curve going up like this. So here the velocity is positive, and the velocity is negative, so that means the object is moving to the left. But if we go and take a look at the slope, you can see the slope is positive. So that tells us that the acceleration is positive. So the acceleration is pointing to the right. And finally, we can do a case where it's sloping down. There we go. Something like that. There we go. So here the velocity is negative, but the slope is also negative. So that tells us the acceleration is negative, which would mean the acceleration is pointing to the left. So this is consistent with what we've seen before. Speeding up, going to the left, the acceleration and velocity point in the same direction. Slowing down and going to the left, velocity and acceleration are anti-parallel. Slowing down, going to the right, they're anti-parallel. Speeding up, going to the right, they're parallel. The way I like to think about it is, for me, I found it useful to say if the acceleration is positive, that means that the velocity is becoming more positive. It means it could either be big negative numbers becoming smaller negative numbers, that would be more positive, or it could be small positive numbers becoming bigger positive numbers, that would work. And if the acceleration were negative, that means the velocity is becoming more negative. That could either be big positive numbers becoming smaller positive numbers, or that could be small negative numbers becoming bigger negative numbers. So that's how I usually try to keep that straight. Now, it turns out that there are 6 prototype graphs that are worth keeping straight. So I'm going to go and divide the screen down the middle like so. So over here we will look at constant velocity. And then over here we'll look at constant acceleration. So let me just make some axes real quick. That'll do. That'll do. Like that. And like that. And then finally, like that. All right. So for all of these, the axes are, here, let me scooch these up just a bit. Oops. Did not mean to do that. There, something like that. And then let's do that again over here real quick. So for all of these, the horizontal axes are time. So let's go ahead and label them T, 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 T. And this is going to be A, V, X, A, V, X. Okay. So if you got a graph of constant velocity, here we go. It might look something like this. The key thing here is that it'll be a horizontal line. Well, the slope of V is 0. So that means that the value of the acceleration would have to be exactly 0. And similarly, if I go and do position, the value everywhere here is positive, meaning the slope of the position graph is everywhere positive. So for constant velocity, position will be a straight line, velocity will be a horizontal line, acceleration will be exactly 0. Now, this could be slid up and down anywhere, or if it's tilted down, then my horizontal line would be negative. But the key features are straight line, horizontal line, exactly 0. Now let's try a constant acceleration. So in case of constant acceleration, that's not 0 because we've already covered that. That would look, whoops, let's try that again. There we go. That would look something like that. So again, the value of the acceleration never changes. So that means the slope of the velocity time graph also never changes. Now here with the position graph, this does mean that the slope changes. Here it starts out a smaller positive value, ends up a bigger positive value. So I'm going to try to draw, this would be a section of a mathematical object that mathematicians call a parabola. And let's try to draw that a little better. Okay, well, I tried. A useful thing to have in your back pocket is if the shape of your parabola is such that it holds water, like this, that will mean that your acceleration is positive. And if the shape of your parabola is such that it spills water, that will mean that your acceleration is negative. Okay, in the next video, we will get quantitative about all of this, so catch you on the flip side.